The James Webb Space Telescope has opened an entirely new chapter in our exploration of the cosmos, bringing with it the potential for groundbreaking discoveries. Just a couple of years after its launch, Webb has already begun reshaping our understanding of the universe, offering unprecedented insights into the formation of galaxies, the nature of distant stars, and even the potential for life beyond Earth. Among the most thrilling of these discoveries is the possible identification of a biomarker on an exoplanet located 125 light-years away in the constellation Leo. This discovery has the potential to answer one of the most fundamental questions that humanity has grappled with for centuries: are we truly alone in the universe? This exoplanet, known as K2-18b, is a super-Earth, meaning it has a mass that's 7 to 8 times greater than that of our planet. Despite its larger size, K2-18b lies within the habitable zone of its host star, K2-18, a cool red dwarf. The habitable zone refers to the region around a star where conditions are just right for liquid water to exist, something essential for life as we know it. K2-18b's location in this zone makes it a prime candidate for hosting life, especially given its potential to harbor oceans. Scientists have long speculated that the presence of liquid water could be one of the key ingredients for life to develop, and the discovery that K2-18b may indeed have liquid water makes this planet a tantalizing target for further study. K2-18b has been on astronomers' radar since its discovery in 2015, but it wasn't until the launch of the James Webb Space Telescope that the true potential of this exoplanet began to unfold. Webb's powerful infrared capabilities have allowed scientists to study the planet in unprecedented detail, particularly its atmosphere. In a groundbreaking observation, the James Webb Space Telescope identified a sulfur compound called dimethyl sulfide, DMS, in the atmosphere of K2-18b. DMS is a compound that, on Earth, is produced by living organisms, particularly marine life such as phytoplankton. The fact that Webb has detected this compound on a distant planet raises the exciting possibility that life, or at least the conditions conducive to life, may exist beyond Earth. While this discovery is not definitive proof of extraterrestrial life, it does offer a tantalizing glimpse of what could be. The presence of DMS is a significant find, as it is an organic compound that is primarily associated with biological activity here on Earth. Phytoplankton in our oceans release DMS into the atmosphere, where it plays a role in cloud formation and the regulation of the Earth's climate. The fact that Webb has detected DMS on K2-18b suggests that similar processes, possibly biological, could be taking place on this distant planet. However, it's important to note that DMS can also be produced by non-biological processes, and the detection of this compound alone doesn't conclusively prove the presence of life. For scientists, the discovery of DMS in the atmosphere of K2-18b is a major breakthrough, but it also raises many questions. Could the DMS be the result of biological activity? If so, what kind of life forms could be producing it? And if not, what other processes could be responsible for the presence of this compound? To answer these questions, researchers have been carefully analyzing the data from Webb's observations, and they are planning follow-up studies to confirm the findings and explore the implications further. Before we delve deeper into the details of this discovery, let's take a moment to consider why the search for life beyond Earth is so important. For centuries, humans have wondered whether we are alone in the universe. From ancient civilizations that gazed up at the stars and pondered the existence of other worlds, to modern scientists who search for signs of extraterrestrial life using advanced telescopes and spacecraft, the question of whether we are alone has captivated our imagination. The discovery of life elsewhere in the universe would have profound implications not only for science, but for our understanding of our place in the cosmos. It would change the way we think about life, evolution, and the possibility of intelligent civilizations beyond our own. The search for extraterrestrial life is not a new endeavor. Over the past century, scientists have developed several methods for detecting potential signs of life on distant planets. These methods typically rely on the analysis of the chemical composition of a planet's atmosphere. For example, astronomers have been looking for what are called biosignatures or biomarkers, specific chemical compounds that could indicate the presence of life. On Earth, these biomarkers include gases like oxygen, methane, and DMS, which are often associated with biological processes. The challenge, of course, is that these biomarkers can also be produced by non-biological processes, which makes it difficult to definitively attribute them to life. For decades, the search for extraterrestrial life has been hampered by the limitations of our technology. While astronomers have been able to detect the chemical signatures of distant exoplanets, they have often been limited by the sensitivity and resolution of their instruments. This is where the James Webb Space Telescope comes in. Webb is a game-changer for the search for life beyond Earth, thanks to its unparalleled infrared capabilities. Unlike optical telescopes, which observe light in the visible spectrum, Webb can observe infrared light, allowing it to detect faint signals that would otherwise be invisible. This ability has made it possible for scientists to study the atmospheres of exoplanets in much greater detail than ever before, revealing new insights into the conditions that could support life. Since its launch in December 2021, Webb has already delivered some truly stunning observations. It has captured detailed images of distant galaxies, provided new insights into the formation of stars, and even allowed astronomers to study the atmospheres of exoplanets in ways that were previously unimaginable. Webb's powerful instruments, including the near-infrared spectrograph, NIR-SPEC, and the mid-infrared instrument, MIRI, have enabled scientists to study the chemical composition of distant planets and their atmospheres with remarkable precision. One of the most exciting findings from Webb's observations is the detection of DMS on K2-18b. This compound, as mentioned earlier, is produced by marine life on Earth, particularly by tiny organisms like phytoplankton. Phytoplankton release DMS into the atmosphere, where it has a number of important functions, including helping to regulate the Earth's climate. The detection of DMS on K2-18b suggests that this distant exoplanet might also have oceans, and if it does, those oceans could potentially be home to life forms similar to the microorganisms found in Earth's seas. However, it's important to note that while DMS is a strong candidate for a potential biosignature, its presence alone is not enough to confirm the existence of life on K2-18b. DMS can also be produced by non-biological processes, such as chemical reactions involving sulfur and carbon compounds. As a result, scientists must be cautious in interpreting the results. The signal detected by Webb was not particularly strong, and there are other potential explanations for its presence. For example, it could be the result of photochemical reactions in the planet's atmosphere, where ultraviolet radiation from the star could break down other sulfur-containing compounds, leading to the formation of DMS. Alternatively, there could be unknown non-biological processes at work that we have yet to fully understand. To explore these possibilities, scientists are conducting further research into the chemical processes that could be taking place on K2-18b. They have already begun creating detailed models of the planet's atmosphere to simulate the conditions under which DMS could form. These models will help them determine whether the observed DMS signal is consistent with known chemical processes or whether it requires the involvement of biological activity. In addition, scientists are planning additional observations using Webb's mid-infrared instrument, MIRI, which is capable of detecting the spectral signature of DMS more clearly. MIRI operates in the mid-infrared part of the spectrum, which is the range where DMS and other organic compounds leave their strongest signals. If these follow-up observations confirm the presence of DMS on K2-18b, it could be a major breakthrough in the search for extraterrestrial life. However, even if the signal turns out to be inconclusive, the fact that we're able to detect such compounds on distant planets is a significant achievement in itself. It shows that we are getting closer to answering the age-old question of whether we are alone in the universe. This discovery also highlights the importance of the ongoing exploration of exoplanets. In the coming years, we can expect more telescopes like Webb to be launched, each one bringing us closer to understanding the conditions that make life possible on other planets. The more we learn about exoplanets, the more we will be able to refine our understanding of what makes a planet habitable and how life might arise in different environments. As the search for life beyond Earth continues, it's important to keep in mind that the discovery of extraterrestrial life, if it happens, is likely to be a gradual process. It may take years, or even decades, of careful observations and research before we can definitively say whether we've found life on another planet. But with instruments like the James Webb Space Telescope and the growing body of data from ongoing space missions, we are steadily moving toward the day when we may finally find the answer to one of humanity's most profound questions: are we alone in the universe? In the meantime, the discovery of potential biomarkers like DMS on K2-18b serves as a reminder of the vastness of the universe and the many mysteries it holds. The fact that we are now able to study the atmospheres of distant exoplanets with such precision is a testament to the incredible advances we've made in space exploration. And as we continue to push the boundaries of what's